Okay, we're going to keep on working with interactions in polynomial regression. And just as a reminder, we defined an interaction to be a term that actually represents the joint effect, the joint um, a contribution of when two variables are together. Um, so we define this beta 3 as that effect. That effect can have an amplifying effect of what x1 and x2 bring by themselves, or they could dampen that effect. When we talk about the effect of a variable now, what we mean is as x1, let's say the effect of x1 on the expected value of y, what we mean with that is that what happens to the expected value of y as x1 changes, and let's say increases by 1 unit. In this case, if there was no interaction, then we would say that the effect that x1 has on the response is that when we increase x1 by 1 unit, then on average, expected value of y increases by beta 1. But now the effect becomes um, beta 1. When x1 increases by 1 unit, then the expected value of y increases or decreases by the effect of beta 1 plus beta 3 times x2. So what that means really is that it depends on the value of x2, where is it held constant. So we're going to take a look more at that, and we're going to use an example. We're going to look at the grandfather clocks example. Remember, this data set is a very small data set that contains the age of the clock in years, the number of beaters, and the price of the clock. Okay, so remember that the regression that we created in this, and let's call it regression 1, we had we used the price as the response, and we use both age and the number of beaters as predictors, and we call, let's say we call these clocks, and then let me show this summary for this. The summary is that it shows that as age increases by the effect of age, so let's call it that now. The effect of age on the expected price is that as age increases by 1 year, on average, the expected value of the expected price increases by about $12.7. So, and as the number of beaters increases by 1, then on average, the price increases by about $86. Now, that is assuming that they don't interact with each other. That um, as the number of beaters increases, then that is not affected by what age the clock has, and vice versa. So what I'm trying to say with this is, let's take a look first on if these two variables interact. And generally, the way that we do this is that we analysts have a suspicion that variables might interact, might have a joint effect. So, for instance, if you think that as age increases, generally the price of the clock increases by about $13, but it kind of depends on the interest of the beaters. So, if there are more beaters, then that effect might change as opposed to having fewer beaters. So in that case, there might be some sort of interaction between the age and the number of beaters. So we can test that by adding that interaction effect. The way that we add an interaction effect is by using the variable and then putting a column and placing the next variable within the LM formula. Now what that does is that it creates that interaction effect right inside the formula, but you could also do this by multiplying the variable age times number of bits of beaters, and then that would be your new variable. All right, so let's do it this way. Let's create now regression 2, and I'm gonna use the LM function using price as a response, and age now and number of bidders as predictors. But now I'm gonna add that age, number of bidders interaction in there, and we're gonna test if it is statistically significant. Again, the data set name is plots. Right, so let's take a look at the summary here. And we look at the summary now, and there's a few things to take away from this. Well, first of all, the interaction is significant. So what that means is that really there is some effect, joint effect, when age and number of bidders are together. In other words, when as we increase age, then the effect is no longer held constant. I mean, it's no longer depends only on age, but it also depends on the number of bidders. Okay, so you can see that the parameter estimates changed dramatically from what they were. In this case, number of bidders even became negative. But now we have to take a look at the joint effect that they have. So let's read it this way. So let me put the code in here, and I'm gonna call these interaction model between age and number of bidders. And I'm gonna just go ahead and paste this so that we can upload it in our code and you can actually practice with it. All right, so what I'm gonna say with, so let's talk about the effect of age now on the price. Well, the effect of age is no longer 0.87, so we can't really say as age increases by 1 year, the average price increases by 87 cents. That is no longer true. We saw before that it was about $12 or something like that. But now it depends on the number of bidders. So really the effect is just this, which is a linear piece of age, plus 1.2978 multiplied by the number of bidders. So really the effect will depend, so the effect will depend on the number, let's say this will depend on the number of bidders. Okay. So we can also say as age increases by 1 year, the effect on the expected price is, so it's going to be just that equation right there. Now that becomes a little difficult to interpret. I mean, when we're doing an interpretation in the language of a problem for people who don't understand or have little knowledge about the problem, that might be a little bit problematic to understand. So we can actually make an example. So let's say that we have, for instance, let's say that we have 10 bidders. Example, if we have, let's say, 10 bidders, then the effect is this: as age increases by 1 year, then on average the price will increase. Let's see, because these two numbers are positive, so we would have to just get that and multiply. It will change by about $13. So let's say we'll increase by that, by about 13.86, which is pretty close to the slope that it originally had. But now you can see that this is dependent on the number of bidders. We can do another example. Let's say if the bidders is 20 now, as age increases by 1 unit, then on average, the price will increase by around 26.83. So we can see now that that increase is steeper when there are more beaters. As the age of the clock is old, I mean, as the grandfather clock is older, and being older with more beaters, that actually does um, increase the expected price of the clock. And now that makes sense because that how steep it changes depending as age increases will depend on what price you have. So we can actually visualize these a little better by doing what we call interaction plots. And interaction plots are actually basically show the slopes. If we had no interaction present, it doesn't matter what the number of beaters are. If we have 5 beaters, the slope is the same. What changes is just the y-intercept. So let's say in the case that we have no interaction, so let's think about this model here. As age increases by 1 year, then on average price increases by about $12.74. It doesn't matter what the number of beaters are, it will always increase by that amount. If we have 5 beaters, the slope is the same. If we have 10 beaters, the slope is the same. 15, 20, so it doesn't matter how many beaters we have. As age increases, the price of the clock just increases by a set amount. Now, having an interaction present means that the slopes are different. They are no longer parallel to each other. They change. So we can see here that if we have 5 beaters, the price doesn't change as much as the age of the clock increases. Maybe that doesn't generate as much interest in the in those actioners. So let's say when we increase the number of beaters, then that makes the change on the price steeper as the age of the clock is, older. So that is what happens with the slope. It just is no longer so the slopes are no longer parallel, and this is what we call interaction plots. These interaction plots are useful. The things that we want to see in interaction plots is how different are the slopes. If the slopes are the same, that just means that there's no interaction between the variables, the pair of variables. But if they happen to be different, one of them seems to be more steeper than the other, or they might even cross, then that is an indication that there is some sort of an interaction present. There are a few packages that help you get interaction plots. And in your notes, I present to you actually 2 different packages. One of them is the interactions package. So you can install it by using install.packages and interactions. Because I have already installed it, I'm not going to do it. So what I'm going to do is I'm going to just load it. So it's the interactions package. And the way that you would actually plot an interaction is if you already have created the regression. So for instance, if you have created the price, age, and number of beaters in that interaction, and you have it already saved in an object such as regression 1, then you can use that interact plot on that object. Just put the the predictor that you want to see on the x-axis, and then you use the PRED, stands for predictor here, that goes in the x-axis, and then you want to put the one that you want to see how it interacts here in the MODX parameter. So let me just give you an example here just to do it. We have already regression 1, that's the object that we created. This one doesn't have the interaction, so it's regression 2 actually. And then I'm going to call the interact plot on regression 2, and I'm gonna use the predictor that I want to see on the x-axis. I can use that predictor, and then that predictor actually is the age. Let's suppose that we want to select the age, and I just have to put it in quotes, and then the MODX, which stands for what predictor you want to have in your, as you know, that interaction, and then you can put the other predictor in there. You can interchange. You can actually select number of bidders here and age in the other. So let me just fix this. So let's call it number of bids here, and that should be enough to create that interaction plot. Okay, so let me just read it so that you can see the way that this particular package works. Is that it actually takes the number of bidders and takes the mean and plus one and minus one standard deviation. So in other words, instead of taking 5, 10, and 15 bidders, what it does actually is that it takes the average number of bidders plus one standard deviation minus one standard deviation, and it plots them so that you can see the differences in the slopes. Remember, if the slopes are the same, in other words, if these three lines are parallel, there is no interaction between age and number of bidders. If we have differences in the slopes, then that is an indication that there is some sort of interaction effect between that pair, those two pairs of variables. So hope that makes sense. This is when we have interactions between two quantitative variables. It is not very different if we have interactions between quantitative and qualitative variables, but it does make sort of interpretation slightly different. So we will see those separately. But for now, things that I want you to keep in mind is that the effect of a variable on the response is going to be what is the combined contribution of the variable, not only from the slope that it has. So in this case, for the effect of age, is no longer just that particular parameter estimate that multiplies age, but it's always every place where you see age belonging to an interaction present. All right, so I hope that helps. We will next move on to an example where we have a quantitative variable interacting with a qualitative variable.